Right, today we're going to have a look at Physics Paper 6, alternative to the practical paper. There we go. And this is for the Cambridge CIE, Cambridge International Examinations, and this is a Cambridge IGCSE. So the paper code is 0625/62, and this is for October-November 2017. Alright then, let's begin.
Let's do this.
Question 1. A student is comparing the oscillations of two pendulums. Figure 1.1 shows the first pendulum. A1. On figure 1.1, measure the distance d from the bottom of the clamp to the bottom of the bob. Alright, so all you have to do is pull out your ruler and measure this distance on the paper itself. Now the answer they are looking for is 5.0 centimeters. Now when I printed it out and I measured it on my paper, I actually got 4.5 centimeters, and that was because the image had been resized by the printer so it could print it onto letter size paper. So be aware, if you're doing this on A4, if you're printing it from a PDF, then there's a good chance you won't get 5 centimeters that it expects you to get, and that's purely because it's not printing out in the same size paper in the same way as it would for the exams itself. Okay, so unless you've got a physical old exam paper, you may well get a different number there, and that's okay. So distance d, 5.0 centimeters, the units are there, so we don't need to worry about that. Part 2, figure 1.1 is drawn 1/10 of the actual size. Calculate the actual distance d from the bottom of the clamp to the bottom of the bob. Well, in that case, that means it's going to be 5.0 centimeters times 10. It's 10 times bigger, and that gives me a distance of 50 centimeters. And again, the unit's sitting there, so it's good to try and remember that. 3. Explain briefly how to use a set square to avoid a parallax, which is a line of sight error when measuring the length of the pendulum. You may need to draw a diagram. Okay, so let's do that. Alright, so all I've done is drawn a little image there of the pendulum, and we've got the clamp at the top, we've got the bob down the bottom. And what we're going to do is draw in a ruler leading from the top of the clamp straight down, and we're going to place a set square up against it. The idea, of course, being that you put the edge of the set square on the side of the ruler and slide it up until it reaches the base of the pendulum. There we go, that's the setup we'd want. We'd want the ruler pushed up against the clamp at the top and the set square pushed up against the ruler. Again, as I say, moved up until it's at the base of the pendulum. So now all I need to do is write down that description. So there we go. Place the edge of the set square on the side of the ruler and slide up until it's at the base of the pendulum bob, and the top of the set square will show the length on the ruler. That's it. B. The student displaces the bob slightly and releases it so that it swings. She measures the time t for 20 oscillations. The time t is shown on the stopwatch in figure 1.2. Part 1, write down the time t shown in figure 1.2. Oh, nice easy question, that one. That's 28.12 seconds, and remember, write in the units, they don't have the units there. 2. Calculate the period t1 of the pendulum. The time period is the time for one complete oscillation. Alright, so what we're going to want to say is that t, the time period for one, is just the time for 20 divided by 20. So that's 28.12 seconds divided by 20. And that gives us a value of 1.406 seconds. Now I'm okay leaving this with the 4 significant figures. Why? Because I've got 4 significant figures up here, and I'm dividing it by an integer. It's meant to be exactly 20 oscillations, or as close as we can get to it. C. The student repeats the procedure using another pendulum as shown in figure 1.3. This is a long, thin pendulum bob. The distance d from the bottom of the clamp to the bottom of the pendulum bob is the same as for the first pendulum. Alright, she determines the time period T2 of this pendulum, and that's 1.37 seconds. In this experiment, both pendulum bobs have the same mass. The student suggests that since both pendulums have the same overall length d and mass, the periods T1 and T2 should be equal. State whether the results support this suggestion. Justify your answer by reference to the results. So the value we got for T1 was 1.406, which give or take is 1.41 seconds. And as you can see, these are actually very close. So the student's saying that they believe that the periods T1 and T2 should be equal. Looking at those values are very close. I would say that the results do support that idea. And I would say that 1.37 is very close to 1.41, so within the limits of experimental accuracy, they're the same. So there we go. Yes, the results support the idea that T1 equals T2. Justification, the value 1.37 is very close to 1.41 seconds. Within the limits of experimental accuracy, they're the same. There we go, and that's good for that. Part D. The period T of a pendulum can be determined by measuring the time T for 20 complete oscillations and then calculating the period. Some students are asked to explain the reason for this method being more accurate than measuring the time taken for a single oscillation. Tick the box next to the sentence that gives the best explanation. Okay, we've got 4 different boxes here. First one, the method eliminates errors from the measurement. Doesn't. There's still errors within the measurement. It doesn't eliminate them. That would mean it gets rid of them. Not at all. It might minimize them, certainly. This method is more accurate because the experiment is repeated. No, it's not. The oscillations are repeated, but we still want to do one experiment now. The third one, the method includes more readings, so there's less chance for errors. No, it's just one reading, but more oscillations. And the last one, the method reduces the effects of errors when starting and stopping the stopwatch. And that's absolutely correct. Because in essence what you're doing is you're getting 20 oscillations, but you only start and stop the stopwatch once. E. A student plans to carry out more pendulum experiments. He considers possible variables and precautions to improve accuracy. In the following list, mark the possible variables with the letter V and the precautions with the letter P. Okay, let's run through this then. Amplitude of the swing is a variable. Length of the pendulum, that's a variable as well. Mass of the pendulum bob is a variable. These are all things that we can change. Shape of the pendulum bob, well, there's 2 different types, so that's a variable. We could easily change it, go to the shop, buy a different pendulum bob. Use of a reference point to aid counting. Well, that's a precaution to mean that our results are more accurate. And viewing the rule at right angles from measuring the length, and that's a precaution as well. That's how we should be using rulers. Question 2. A student is investigating the cooling of water. A. The thermometer in figure 2.1 shows room temperature, theta r, at the beginning of the experiment. Record theta r, so record the reading on the thermometer. Now looking at that seems to me to say 24 degrees Celsius. And looking there, the units are already in. B. The student pours 50 centimeters cubed of hot water into a beaker. He measures the temperature, theta h, of the hot water and gets 86 degrees Celsius. He adds 50 centimeters cubed of cold water to the beaker. He stirs the water briefly. He measures the new temperature, theta m, of the water in the beaker and gets 52 degrees Celsius. Calculate the temperature fall, theta f, using the equation theta f is theta h minus theta m. Alright, easily done that. Here we go, theta h is 86 degrees Celsius minus theta m, which is 52 degrees Celsius. And putting that into the calculator gives us a value of 34 degrees Celsius. Remember your units, it's not written down here. He repeats the procedure in B using 100 centimeters cubed of hot water and 100 centimeters cubed of cold water. And there we go, we get theta h value and a theta m value again. Calculate the temperature fall theta f using the equation theta f is theta h minus theta m. Alright, well theta h is 84 degrees Celsius minus theta m, which is 54 degrees Celsius, and that's 30 degrees Celsius. And again, remember the units. D. Suggest one reason for stirring the water before reading theta m. Well, we're adding two different temperatures of water. What we want to do is ensure that the water temperature is uniform. E. A student states that the temperature fall theta f should be the same each time because the proportions of hot water and cold water are the same. Suggest one reason why theta f could be significantly different in parts B and parts C. Well, we got two different volumes of water being added together. There's a very good possibility that what's going to happen is if there's any time delays, there's going to be heat loss to the surroundings. And that's something, of course, that heat loss to the surroundings is something we'd have to take into account and try and isolate the system from that happening. F. Suggests an improvement to the apparatus to make it more likely that theta f would be the same each time. Well, you know what? Talking about heat loss, how about putting some insulation around it? There we are. Use insulation to reduce heat loss. G. Suggest a condition not included in your answer to F that you would control to make it more likely that theta f would be the same each time. Right. I think one of the main things to do would be to control, say, the starting temperature of the hot water and the cold water. There we are. So we'd want the hot water to be the same temperature both times, and we'd want the cold water to be the same temperature both times. So the starting temperature for those two to be the same. H. The student uses a measuring cylinder to show the volume of water he uses. Draw a measuring cylinder about half full of water. Show clearly on your diagram the line of sight required for obtaining a correct reading for the volume of water. Okay. And there we go. What you can see I've labelled is the meniscus. Oh, let's put a couple of arrows there, it looks a bit weird. The liquid, the measuring cylinder, and the eye. And we can see the eye is viewing at a 90-degree angle. Now, just to make sure there's no ambiguity, it's a measuring cylinder. Let's just put a little scale there. There we are. Beautiful. Fantastic. All right. That's perfect. Let's move on to the next question. Question 3. A student is determining the focal length f of a lens. Figure 3.1 shows the apparatus used. So we've got a lens, an illuminated object, and a screen on the other side. A. The student places a screen about 100 centimeters from the illuminated object. She places the lens between the object and the screen so that the center of the lens is at a distance of u equals 20 centimeters from the object. She adjusts the position of the screen until a clearly focused image is formed on the screen. She measures the distance v between the center of the lens and the screen. She repeats the procedure using values of u of 22, 25, 30 and 35 centimeters. The readings are shown in table 3.1. And there we go, there's table 3.1 with the different readings for u and v. Plot a graph of v in centimeters on the y-axis against u in centimeters on the x-axis. You do not need to start your axis at the origin and draw the best fit curve. Alright, so there's two key points here. One, you do not need to start your axis at the origin. That means you can have a jump in the axis. And two, it's asking to draw the best fit curve, not a straight line. And that's quite important. If for no other reason than when I'm trying to do this on the computer, it's going to look terrible. But that's irrelevant, so it's asking for you to draw a curve as you do this, not a straight line. Alright, so let's sort out our axes. Alright, so they're the axes, I've done them out. We have v on the y-axis against u on the x-axis as the question requests. And I've done a little jump in the axis at the start. So now let's put the points in. So there we go, that's the points now plotted. We've been asked to draw a best fit curve. It's going to be tricky. Let's see if we can get one in. And there we go, not bad. Alright, let's move on to the next part of the question. Right, B1. Mark with a cross the point on the graph grid where u equals 25 and v equals 25. Okay. And mark with a cross the point on the graph where u equals 35 and v equals 35. And then after that, join these 2 points with a straight line. And part 2, record u1, the value of u at the point where the straight line crosses your graph. Now that looks to me like the straight line crosses the graph when u equals 30. Straight down there. So that's our u equals 30. Record v1, the value of v at the point where the straight line crosses your graph. And interestingly enough, that looks like it's 30 again. If I follow this line across, there we are, comes out at 30, it's exactly where it crosses, so it's 30 as well. So it's 30 as well. Part 3. Calculate the focal length f of the lens using the equation f equals u1 plus v1 divided by 4. Alright, let's put that through. So f equals u1 plus v1, that's 30 centimetres plus 30 centimetres divided by 4, which is 60 centimetres divided by 4, which is 15 centimetres. There we are. And of course we've got our units here. And good to pop back and check to make sure that you've got your units down. There we are. C. Suggest 2 differences you would expect to see between the appearance of the illuminated object and the image on the screen. Well, first one, of course, the image on the screen will be upside down. So the image is inverted. And the second one, of course, is that the image on the screen will not be as bright as the illuminated object. D. Suggest 2 precautions that you would take in order to obtain reliable readings in this experiment. Alright, well, first one, as always, use a darkened room. It's important. It's very difficult to see this clearly unless the room is dark. And 2, move the screen slowly backwards and forwards to get the best image. And there we go. So use a darkened room, move the screen backwards and forwards slowly to get the best image. Now, surprisingly, one of the ones that I like to use a lot, which is to put a mark at the centre of the lens holder so you can measure the distances more accurately, does not come up in the marks scheme this year, or for this particular year. So that's a surprise. But there's 2 very good ones that you can use. Question number 4. A student has a selection of rubber bands of different widths. He is investigating the extension produced by adding loads. Figure 4.1 shows the setup used. So there we go, we can see we've got a clamp boss and stand, there we go, and we've got a rubber band with a hook hanging off it over the edge of a bench. In addition to the apparatus shown in figure 4.1, the following apparatus is available to the student. A meter rule, a selection of different rubber bands, and a selection of loads. Plan an experiment to investigate how strips of rubber of different widths stretch when loaded. You should explain briefly how you would carry out the investigation, state the key variables that you would control, draw a table or tables with column headings to show how you would display your readings, and you're not required to enter any readings into the table, and explain briefly how you would use your readings to reach a conclusion. Alright, so let's go up and look at that picture again and maybe analyse a bit about what we can do. Okay, so it looks to me like what we're going to be doing is hanging weights off the bottom of the hook, or in this case, let's just examine it a little bit more. Rubber bands of different widths, that's what we're investigating. Got a selection. So maybe rather than hanging different weights, we hang one weight of different thicknesses of rubber band and see how they compare in terms of how much they stretch, how much they extend. Now, let's run through that and see what we can come up with. So, well, steps, and it's always good to do a rough kind of little sketch out about what you're thinking about here. So if I look at how I'm approaching this, how I'm thinking. So first I'm thinking probably set up the equipment. That'd be my first thing. Second thing would be, well, add weight. And 3, record the extension. They're going to be the key points. And then 4, change band. Alright, so that's my rough idea of what I'm thinking of. Now, let's put in some key things. For the extension, I'm going to need to measure the length. The original length. And I'm also going to need to measure the stretched length, the new length. Where it's holding a load. Now looking at that, I'm going to say, okay, well, different bands of different lengths are going to stretch different amounts anyway. Okay, so a key point then would be to have a fixed length of rubber band. Say 20 centimeters. So I say 20 centimeters, why not? Fixed length of rubber band, measure the length, the original length, then we add weight. Now the fact I'm setting up a fixed length of rubber band means that I don't need to measure the original length, I'd have to measure it as I'm putting it in. So I can take that second part there out. And for changing the band, it's going to be changing the width. We're probably going to want to see 5 or more different bands. Different widths. Now, as we're the ones setting up the experiment, let's just say 5. 5 different bands, 5 different band thicknesses. Alright, so this represents the experiment we're looking at doing there. Now, what I'm thinking of doing, I'm just thinking of adding 1 weight and taking 1 measurement for each different band. Why not add a whole selection of weights? Well, because I've already got a whole selection of bands. And I want to be careful to restrict the experiment so I can get the most meaningful information out of it in the shortest period of time. So I think 1 weight across different bands is utterly acceptable. So looking at this, I'm going to need to measure the original length and I'm going to need to measure the new length and find the extension. So I'm also, if I'm going to be doing all these measurements, I'm going to need a meter rule and have that set up so I can measure the length from the top of the clamp. Okay, so that should sum it up, that should do quite nicely. Let's start putting that information down. There we are. So the first step is going to be set up the equipment as above, use a 20.0 centimeter length of rubber band, use a meter rule to measure the original length from the base of the clamp. Okay, so at that point we've got a fixed length of rubber band, which is something that we were after. And then what we can do, of course, is we can add a weight or a mass to the bottom of the rubber band. We can measure the new length. 2. Add a 100 gram mass to the hook at the base of the rubber band and record the new length of the rubber band in the table. We'll write down in the table. Now once you've done that, of course, you're going to want to calculate the extension of the rubber band. So let's put those steps in. So we're recording the new length of the rubber band in the table. Step 3, calculate the extension of the rubber band. Now, of course, step 4, what we're going to do is change the rubber band and perform steps 1, 2 and 3 again. Something that I've noticed, because I'm writing this out in sections, is straight away I've noticed I haven't measured the width of the rubber band, so I'm going to have to put that in there. Maybe step 1. Let's have a look. There we are. So what I'm going to want to do is add to step 1, measure and record the width of the rubber band, the unloaded rubber band. So measure and record the width of the unladen rubber band in the table below, and at the end of this I'll put a little table that I'd like to use to record all the information. So our final step, step 4, will be Replace the rubber band and repeat steps 1, 2, and 3. Repeat this for 5 different widths of rubber band. There we go. So replace the rubber band with one of a different width. Repeat steps 1 to 4 for 5 different widths of a rubber band. Now let's design the table we want to use. So there we go, there's my table. I'm going to record the original length of the rubber band, L0 in centimetres, and that should be 20.0 for all of them. In fact, you could even fill in that column there, that's not a problem. The next column, length of the rubber band with a 100 gram load. Then after that, the extension of the rubber band, and it's quite important, I think, to show how we're calculating the extension. And then finally, the other bit of information that's very important for this experiment, the width of the rubber band. And I've got the units for all of those up in the top as well. So you know what I might do? I might actually write in the value of the original length of the rubber band. There's no, in fact it told me that I didn't have to in the question at all. The only reason I'm doing that is to make sure that they know that that's a controlled variable. There we go, no need to do that, but it just makes me feel a bit more comfortable with the knowledge that I'm saying this is what it will be, or what it should be, certainly. Okay, so let's move on to the last part. How do we analyse these results? So we have a table there showing a lot of information. What we're going to want to do is compare the extensions of different thicknesses for the same load. So there we go. Using the results in the table above, compare the extensions of different thicknesses for the same load. That's it. Now I could do a variety of different weights, different masses for the different bands, but that's a little bit of overkill. I've already got 5 different bands, thicknesses of bands being measured. I don't want to then pull in another 5 different masses and draw graphs all over the place and I start analysing the gradients. I could do that, but it's much more straightforward as I've got 5 different values of one thing already to use one mass, one weight. So I'm using a reasonable one. I think 100 grams is a good value, and that should give a reasonable extension across the rubber bands. So there we go. That's it. Well done. We've reached the end of that paper. So hopefully you found that useful. If you did, please feel free to like and subscribe, and feel free to leave us a comment in the comment section below. You know what? Have a great day.